All right, we're going to talk about absolute value equations and inequalities. So these are any type of problem where you have an absolute value and you have an equal sign or a less than or greater than sign. So let's look at our first example here. So we've got the absolute value of 2x minus 1 is equal to 7. And before we actually do this problem, I just want you guys to do a thought exercise with me for a minute. I want you to imagine I have the absolute value of something. I'm literally going to write something because I don't know what that thing is, but it's something. It's in there. If the absolute value of that thing was 7, I have a thought. And that thought is that either the something must be itself 7, or what's the only other possible value that something could have? Hopefully you said -7. Because the only way for me to take the absolute value of something and get 7 is for the something in here, this thing in here, is either +7 and I take the absolute value of +7 and I get 7, or you take the absolute value of -7 and you get +7. So my thought here is that whatever's inside your absolute value either straight up equals this thing or it equals the negative version of this thing. And that's how you do absolute value equations, basically. There you go. So all we're going to do is we're going to make two cases. Sometimes I will draw like an arrow here. The first case is that the thing inside the absolute value, the something, if you will, is equal to 7. That's the first case. The other case is that the thing inside the absolute value, 2x minus 1, equals -7. And that's about it. So we're going to solve here. So on this one, I'll add 1 to both sides. I'm going to do the one on the left here first. Get 2x is equal to 8. X is equal to 4. Okay, that's one of our solutions. How about the other one here? If we add 1 to both sides, we'll get 2x is equal to -7 plus 1 is actually -6. So x is -3. Okay, so those are our two solutions. It's really helpful to check them and make sure they work. So let's just take a moment and check them. I know it's annoying, but let's do it. So if we do the absolute value of 2 times 4 minus 1, do we actually get 7? So a lot of times I'll put equals with a question mark, 7, as I slowly work it out. So this will be 2 times 4 is 8 minus 1 is 7. So is the absolute value of 7 equal to 7? I think it's safe to say that that works. How about -3? Let's go over to -3. So we're going to do the absolute value of 2 times x, which is -3, minus 1. And that's supposedly equal to 7. I'm not sure if it actually is. That's what we're doing right now. Okay, 2 times -3 is -6. And then if you subtract 1 from that, well, let's not skip that step. So the question is, are these actually equal? The absolute value of -6 minus 1, is that actually equal to 7? So if you do -6 minus 1, you get -7. And the absolute value of -7, is that actually equal to 7? It is. Cool. So both of those work. Okay? So that's one example of how to do an absolute value equation. Let's do another one here that's slightly more complicated. On this one, you've got 2 times the absolute value of x minus 3, and then you finish the absolute value, and then you subtract 1, and that's equal to 9. So generally what you're going to want to do on these is get the entire absolute value part by itself. A lot of people are tempted to say, oh, well, this whole thing must equal 9, or it must equal -9. And that wasn't the argument from before. The argument was if I had something in the absolute value bars and it was equal to just a number, then I could say that the stuff inside the absolute value bars was either equal to that number or the negative of that number. Okay, so let's get the absolute value by itself. So I'm going to add 1 to both sides. And that will give me 2 times the absolute value of x minus 3. Those will go away, is equal to 10. and I will divide by 2 on both sides here. So now I'm left with the absolute value of x minus 3 is equal to 5. Now I can make my two cases, and that's what I'm going to do. So the first case is, look, if the absolute value of something is 5, then that thing must straight up equal 5. Or the thing inside the absolute value, which is x minus 3 in this case, is equal to negative 5. Those are the two cases. If you add 3 to both sides here, then you'll get x is equal to 8. If you add 3 to both sides here, you'll get that x is equal to negative 2. Okay, so those are our solutions. For the sake of time, if you just believe me, they both work. So I'm not going to check them. However, I do want to say one thing about when we write solutions for solution sets, it's really important that we do it correctly. My algebra teacher always used to take points off for this, and it drove me nuts. So on this first solution, on this first problem, we had 4 and negative 3 as solutions. So what we do is we put these curly brackets and we say x is equal to, and I usually like to list the lesser number first. So that's our first solution set for that first problem. For our second problem here, we want to say that our solution set is curly bracket x is equal to negative 2 comma 8 with closed curly brackets. So that's going to be our solution set for those. Okay, let's talk about another example here. So we've got 2 times the absolute value of x minus 5 is equal to 4x. So again, I'm going to recommend get that absolute value by itself. So we'll divide by 2 here on both sides. And so we'll have the absolute value of x minus 5 is equal to 4x divided by 2 is just 2x. Now we've got, this is a little different from the last ones. We've got the absolute value is equal to not a number but another variable expression, so 2 times x. If it was just 2, we would, say equals 2 or negative 2. But this is a little weird because we got a 2x. So what we're going to do is we're going to do the exact same thing. We will take two cases. Either the x minus 5 straight up equals the 2x, or the x minus 5 equals the negative version of that. You don't really need the parentheses here, but I'm just putting them there for effect. Because if I had something there that, if I had like x squared plus 1, you would have to put the whole thing in parentheses and then take the negative of it. So, all right. On this one, let's see, if I solve for x here, I'm going to actually subtract x from both sides. And so when I do that, those go away. I'm left with negative 5 is equal to 2x minus x would be just 1x. So x is equal to negative 5 here. That's one of the answers. And let's see, how about the other one here? So the other one, I'm just going to rewrite as x minus 5 is equal to negative 2x. And then let's see, if we're solving for x, personally, I would add 2x. Again, I like to have positive variables. So if I add 2x to both sides, I'm left with 3x minus 5 is equal to, there's technically 0 left over here, so I'm going to add 5 to both sides. And so we'll get 3x is equal to 5. So x must be, if you divide by 3 on both sides, you'll get x is 5/3. Now, one of the important things here in checking your solutions is that when you actually check this, it doesn't work for one of the solutions. So let's go back up and, sorry, I'm making you guys seasick here. Let's take our original equation. So it's 2 times the absolute value of x minus 5 is equal to 4x. And let's scroll down here and let's try both of these in that. So 2 times the absolute value of x, which in our case, I'm going to do x in orange. So x minus 5 is equal to 4 times x I just want to scroll up and make sure I got that right. 2 times the absolute value of x minus 5 is equal to 4 times x. Okay? All right, so we have taken our second solution here, and we've substituted the solution that we got back into the original. So it was 2 times the absolute value of x minus 5 is equal to 4 times x. Let's see if this is actually true, because we're not claiming that it's true. We're just double checking to make sure it's true. So we're going to do 2 times the absolute value of, let's see, negative 5 minus 5 would be negative 10. And supposedly this is equal to 4 times negative 5, which let's just say that that's negative 20. Now we've got 2 times the absolute value of negative 10 is positive 10. And the question is, are these equal? And you're probably starting to see, 20 is not actually equal to negative 20. Those are not equal. So the problem here is with algebra, we got a solution of negative 5, but for whatever reason it doesn't work. And I suspect that part of that has to do with if you actually plug in a negative number up here. If you plug in a negative number up here for x, what you'll get is you'll get that the absolute value of something is negative, and that's dumb. You can't have the absolute value turn out a negative number. Let's try the other solution here. So we've got 2 times the absolute value of, this is going to be messy, 5/3 minus 5 is supposedly equal to 4 times 5/3. Okay, all right. I'm going to draw some lines here just so we can see what's going on. All right. So 2 times the absolute value of, if you do 5/3 minus 5, let's see, 5/3 minus 5, 5 can be written as 15/3. So really, 5/3 minus 15/3 would be negative 10/3. So this is going to be negative 10/3 here. Supposedly that's equal to, let's see, 4 times 5/3. You can just multiply the 4 and the 5, so you get 20 over 3 here. So now we've got 2 times the absolute value of negative 10/3 is just positive 10/3. And supposedly this is equal to 20/3. And this one, it looks like, is going to actually work out nicely. So 2 times the 10/3 there will give us 20/3. And is that actually equal to 20/3? Well, yep, it sure is. So what that means here is that the actual solution, I don't know why when I scroll it's catching my text here. The actual solution here, when we write this, is only going to be x is equal to 5/3. That was our one solution that worked here. All right, so that's that one. Let's scroll up here and do another example. Number 4 here. So we've got the absolute value of 3x minus 1 is equal, plus 4 is equal to 1. So like I recommend, get that absolute value part by itself. So we've got the absolute value of 3x minus 1 is equal to, that goes away, negative 3. Now, I want you to think about this for a second, because if you try to solve this, you're going to get a couple solutions that make absolutely no sense. So I want you to catch this before you try to solve it and waste your time. Okay? If you have the absolute value of something and it returns a negative number, that doesn't work. When you take the absolute value of something, if that thing is positive, then you just get a positive number. If this thing inside here is negative, then you would still get a positive number, right? So this is not possible. If you get something like this, you can immediately just write no solutions. Okay? Because you can't have a negative value when you plug in an absolute value. So let's go to some pointers for you guys for working through absolute value equations. So here's your advice. Number 1, get the absolute value part by itself. before you create two cases. Okay, so make sure you get the absolute value bars all by themselves. It's just like when you solve something for x, except the whole absolute value part is kind of your x, if you will. Second tip is check your solutions to make sure they work, and which is everybody's least favorite thing, and people always forget to do it. And third is if you get a solution with perfectly fine algebra, in other words, if you did the algebra right, but it doesn't work when you plug it into the original equation, it's called an extraneous solution. That's what we call those. We had one of those a minute ago. -5 was our extraneous solution on that third problem there. Okay. And then, I just put a little note here. They're probably the most annoying thing in algebra 2, maybe with the exception of pop quizzes. Okay. So when you get an extraneous solution, what you'll do is, you remember on that last problem where we had, we solved it out and we had x was -5 and also x was 5/3. We found out that this one worked, but this one didn't work. So when you get an extraneous solution like -5, you'll just leave it out and you'll say, hey, this is the only solution that actually works. Like, this is my solution. Now let's move on to absolute value inequalities. So let's take this first example here. So I'm going number 5 because I just did number 4 with the equations there. We're going to treat this very similar to how we treated the equations. So what we're going to do is we're going to make two cases, and the first case is just going to be straight up 2x minus 1 is less than 7. And then the other case, many of you probably guessed this just from an intuitive standpoint, we're going to flip the sign and negate it. So we're going to say 2x minus 1 here is going to be greater than -7. And then what we're going to do is we're just going to solve each one of these inequalities separately. So the first one I'm going to solve, add 1 to both sides, we get 2x is less than 8. Divide by 2 on both sides, you'll get x is less than 4. So that's one solution. The other solution here is we'll add 1 to both sides. We'll get 2x is greater than -7 plus 1 would be -6. If you divide by 2 on both sides, you'll get x is greater than -3. So that's a solution. On a problem like this, you have a couple inequalities here. You have x is less than 4, and you also have x is greater than -3. You're going to do an and here. You're going to do x is less than 4 and x is greater than -3. And I'm going to talk about how to decide whether or not you're going to use an and or an or for this word right here, because it really changes the solution set for this. Okay, so we're looking for numbers that have to be greater than -3 and less than 4. So the numbers that we pick have to fall, they have to be both at the same time greater than -3. So they're going to have to be greater than -3. So they're going to have to be somewhere along this line. They also have to be at the exact same time less than 4. This is not the answer here. I'm just showing you visually. I want you, sometimes this helps me visualize. Okay, what am I looking for? Okay, all right, so we've graphed the greater than -3. We've also graphed the less than 4. And what you'll find here is that you're looking for places where these arrows intersect each other, because we need both of them to be true. The only place where they actually intersect each other is this middle part, this green area in the middle. So our final solution here, in this case, is we'll draw a number line, we'll put the -3, and we'll put the 4. And our solution here is open dot, and we'll just shade right in between. So that's our solution. Okay, don't worry about this. Just disregard this guy right here. But this is your solution. If we go with interval notation, we will say we'll start at -3 with a parenthesis because we're not including it. And we'll go until 4 with another parenthesis because we're not including that either. Okay, so this is interval notation. And then set notation. We'll say for this, we'll say, hey, we'll take any values of x in the real numbers as long as Okay, we need x to be greater than -3 and less than 4 at the same time. So a lot of times I'll just pick the the lower number here, and by lower I mean further left. So -3, and then I'll do less than x. So that means x needs to be greater than that number, and then x needs to be less than that number right there. Okay? All right, so that's how you would solve that inequality. Let's do its neighbor here, and it's slightly different. The only, well, there are a couple things different, but what I want you to notice here that's different is this one has the inequality is, the absolute value is less than 7. This one here, it's slightly different. It's x minus 4 instead of 2x minus 1. But this one's going to be greater than 7, and what happens is it changes it fundamentally when we do that. So let's go ahead and solve it out. So we've got two cases. The first case is that x minus 4 is just straight up greater than 7. The second case is x minus 4 is less than -7. So you flip the sign and you negate the number. Okay, and then if you solve these pretty quick and easy, you'll get x is greater than 11. So that's one of our solutions. Our other solution is if we add 4 to both sides, we're going to get that x is less than -7 plus 4 is -3. And so now we've got a couple inequalities. This is going to take an or instead of an and. So what we're going to say here is that we're going to say is x is greater than 11 or x is less than -3. And I'll walk you through kind of why that is in just a minute. But let's actually go ahead and graph this. So we're looking at the graph of x is greater than 11 or x is less than -3. So we only need one of those conditions to be true. I'm going to throw -3 down first, and then I'll put 11 over here. So I need it to either be less than -3, so anything over here would make that work, or greater than 11, which means anything over here would work. So this is your solution if you're going to graph it. And then let's go ahead and write out interval notation and set notation. So interval notation on this one would be, okay, so we need to start, what's the lowest number we go to? I'm going to say if we are looking at this, this goes all the way back to -infinity. So we'll say -infinity all the way up until -3. Now the question is, should we include -3? I'm going to say no, because it's saying x has to be less than -3. It can't actually equal -3. So that means we'll put a parenthesis here. Remember, when we have two things, but they're an or, we put this little union sign here. That little union sign here, the U, just means, hey, it's either in here or it's in here, which we're about to write. Okay, so we're not including 11, so I'll put a parenthesis there, and then we'll put 11, comma, all the way up until infinity. That's interval notation. Set notation. We're going to say, hey, we'll take any x in the real numbers, provided that x is less than -3 or x is greater than 11. Don't forget to close off the bracket there. Okay, so that's how you do that one. So I promised I'd talk about how do I know if it's an and or an or, and why would I use an and versus an or. Okay, and so here's a little, just for those of you who like your notes. If the absolute value is less than some number, so in other words, if you have something like x minus 3 is less than 6, that's going to result in an and inequality. Okay? If the absolute value is more than some number, so like if x minus 3 happened to be greater than 6, this is going to result in an or inequality. Okay? Which begs the question, why? And basically the answer has to do with what absolute value means. Okay, so I want you to think about the following situation. If I said the absolute value of x was less than 4, what would that mean? So let's think about this on a number line. Absolute value is just distance. Okay, so if the absolute value to my number was less than 4, and that absolute value is the distance from 0. So I want you to think if you're at 0 and the distance to my number is less than 4, then that means that I can only reach out to 4 here, or I can reach this way 4, but if I go that way 4, I'm technically at negative 4. Anything in this green zone is fine, right? The distance, if you took any point in this green zone and you took its distance to 0, it would be less than 4. But if you get outside of the green zone into the red zone here, then you're going to deal with places where this inequality becomes false, right? Like if you took 5, the distance between 5 and 0 is 5, which is greater than 4. So what happens here is when you get absolute values that happen to be less than a certain number, it creates these situations where you have a zone, like a habitable zone, to use a science term, where the inequality can be true. Inequalities like this happen to have the and nature to them, right? So it's greater than negative 4 and it's less than 4. Okay, so these arrows, don't be confused. I drew them to indicate that we are starting at 0, going out to negative 4 and out to 4. These arrows actually, if you think about this inequality, if we were going to shade, we would shade everything above negative 4 and everything below 4, and we would say, hey, it has to be greater than negative 4 and less than 4 at the same time. Vice versa, if you go the other way, if you take the absolute value of x and say it has to be greater than 4, then that means that the distance between your point that you're interested in and 0 has to be more than 4. So that means that our distance is going to need to be at least, not at least, it has to actually be more than 4. That means that the good zones now are the green parts and the bad zone is now the red part. The only way that you can get an inequality that provides a graph like this is if you have an or, right? You have to say, hey, x needs to either be less than negative 4 or x needs to be greater than 4. That's how I kind of mentally remember how those work. All right, let's move on to one last example of an absolute value inequality. So we've got this inequality here, which is the absolute value of 2x plus 3 is less than negative 16. And just like the absolute value equation, I want you to think about these before you solve them. I want you to think about this for a sec. The absolute value of something is less than negative 16. Well, the absolute value is just distance. The distance can never be, well, unless you're in like some conceptual applied physics class where there are exceptions. The distance has to be positive. So before you even try working on this, you can just say no solutions, because the absolute value has to be at least 0. Absolute values can only work if the number over here is like greater than 0. Okay, so you can't take anything where you have a negative value.